Calculating the distance around a shape sounds like a fairly simple task. We take the length of each side and add them all together. Easy enough. But in real life, we don't always have access to the length of every side, or we're dealing with complicated shapes, like wonky rectangles or circles, or even some combination of shapes. So, sometimes calculating the distance around a shape involves a bit of logic to determine the missing information. Fortunately, when we understand the relationships between different shapes and lengths, we can use that to find the distance around any shape. And it's all based on knowledge humans have relied on to build and travel and design for hundreds or even thousands of years. I'm Jason Guglielmo, and this is Study Hall Real World College Math. The length of the boundary around any two-dimensional shape is called the perimeter. The word comes from the Greek word peri, meaning around, and metron, which means measure. So literally, if we measure around any two-dimensional shape and add up our measurements, we get the perimeter. But like we said at the start, sometimes those measurements aren't easy to find. Like take the predicament Naikima and Carla find themselves in. They're organizing a march for disability awareness and are trying to identify the best local park for the event. The ideal location will need to have a green space for registration and an outer boundary that's long enough for marchers to do a couple of laps without walking for too long. In their area, there are 3 parks that might meet their needs. A park with a trail that loops around rectangular green spaces, a park with a green space in the shape of a circle, and a third park that seems like a funky blend between the shapes of the other two. Since all 3 parks have a green space, Naikima and Carla need to find the distance around each of the parks to make their final decision. The first park is known as the 4 Greensboro Corners, probably in part because its green space and parking lot are enclosed by 4 corners. It has a trail that outlines the shape of the park starting at the northwest corner of the parking lot. It heads north up McCain Boulevard for about 4 yards, then goes along Richmond Avenue for 14 yards, south down McNeil Drive for 11 yards, and then after 8 yards on Cousin Street, it kinda loops back to the beginning in the parking lot. But the map doesn't show the length of the parts of the trail that touch the parking lot. Remember, based on the literal meaning of the word perimeter, if we had all the measurements, we could just add up all the sides and boom, perimeter. This would be especially easy if the park was a perfect square and each side was the same. We just need to measure one side. Or even if the park was a rectangle with 4 90-degree angles and 2 sets of equal parallel sides. That isn't the case here. But thinking about squares and rectangles is still helpful because they have some key relationships between their 4 sides that we can use here. Since all of the trail segments are straight, parallel to some road, and make right angles where they meet, Naikima and Carla can infer some things. First, let's try to figure out the length of the trail segment that's parallel to Richmond Avenue and Cousin Street. If this park was a rectangle or square, the trail parallel to Richmond Avenue would also be 14 yards, since opposing sides of a rectangle are equal. But here, that 14 yards has kind of been broken up into chunks. First, we go 8 yards along Cousin Street, then we go up, then we continue along parallel to Richmond Avenue. So the 8-yard segment along Cousin Street plus the west-east parking lot segment should add up to 14 yards. 14 minus 8 is 6 yards, so this segment is 6 yards long. Then we can do the same thing for the other unknown sections of the trail. If the park was a rectangle or square, then the part of the trail that's parallel to McNeil Drive and McCain Boulevard would also be 11 yards. We know the part along McCain Boulevard is 4 yards, so the unknown section is 11 minus 4 yards long. So even though Naikima and Carla weren't dealing with a simple rectangle or square, they could still use what they already knew about those shapes to help them out with something a bit wonkier. Altogether, the total length of the trail around the green space is 4 yards plus 14 yards, plus 11 yards, plus 8 yards, plus 7 yards, plus 6 yards. That's a perimeter of 50 yards long. The second park they're considering is called Revolution Park, and it has a green space in the shape of a circle with a sidewalk running along the outer boundary. And even though there aren't any right angles here, we can still use what we know about other shapes and measurements to help us figure out the perimeter. With circles, the length of that outer boundary has a special name and is called the circumference. This time, since the circumference of a circle is the length of a curved line, they can't depend on the streets around the park to be that helpful. But say we unravel the circle so that the circumference is just a single flat line. Then we could measure that length and get the circumference. This trick might come in handy in smaller situations, but unfortunately we can't always unravel a circle just to measure its circumference. Like here when we're dealing with a big park. But thinking about unraveling circles is one way to figure out a pattern for calculating circumference. And it's something we can all do at home with smaller circles. Here, Nikema and Carla can't unravel Revolution Park. And we can't just add up all the sides like we did with 4 Greensboro Corners Park because, well, there aren't really any sides here. But with a little historical ingenuity, we can kind of combine both these strategies. Back in the day, a guy known as Archimedes of Syracuse was sketching all types of circles. Wheels, pizzas, coins, Roombas. Despite the fact that some of these circles didn't exist around the year 250 BC when Archimedes was working, he wondered what number of sides a polygon needed to have to look like a circle. We knew how to find the area of a polygon that was nothing but straight lines, but the circle was not as straightforward. So he draws a round shape. Then he tries to draw polygons with more and more sides inside that circle. He made polygons with hundreds of sides fit inside the circle without changing its circumference. In fact, Archimedes of Syracuse wasn't the only person who wanted to figure out how to measure the distance around a circle. In China, Zhu Changzi drew a polygon with 24,576 sides inside of a circle. The more sides they added, the closer they could get to the actual circumference of the circle. Now, throughout their explorations, they also measured other aspects of their circles, like the diameter, which is a line segment that joins 2 points on a circle and passes through its center. And what we can notice is that as we add more and more sides to the polygon inside our circle and get closer to the true circumference, the number we get is about 3 times the diameter plus a little more. This is also what we notice if we unraveled a bunch of circles. Even though there was no way for them to know each other, Archimedes and Zhu Changzi were both calculating a relationship between the circumference of a circle and its diameter. And that relationship relies on the quantity we call pi. Archimedes calculated pi being something between 3 1/7 and 3 1071. Both values come to 3.14 when we round to the nearest hundredths place. Zhu Changzi's calculations, on the other hand, let him calculate pi out to 6 decimal places. Today, we know that pi is a universal constant with an infinite decimal point that we often round to about 3.14. And often, we use the lowercase Greek letter pi as the symbol to represent this constant. Regardless of the exact number they used for pi, it turns out the values Archimedes and Zhu Changzi were using were close enough that the patterns they'd found were holding up no matter how big or small they would draw their circles. So for every circle, there is a universal relationship. The circumference equals pi times the diameter. And while we've just given the highlights here, I encourage you to look up the full proof of the relationship between a circle's circumference and diameter and pi. Ancient mathematicians discovered the value of pi and its relations to circles by drawing other shapes inside and around a circle, which is pretty cool. Knowing this relationship and exploring it with smaller circles makes calculating the circumference of Revolution Park much easier for Nikema and Carla. Without even having to visit the park, they can measure its diameter because it's pretty much the length of the street that runs along the outside of the block the park is within. That distance can be found using a map, and it turns out the diameter of this park is 22 yards. Then they multiply that diameter by pi, and they get a circumference of a little over 69 yards. Even though circles look a lot trickier than shapes with straight sides, we can use what we already know about other shapes to help find underlying relationships. A lot of math is just looking for the patterns that show up all around us. Finally, Dunkley Park is the last park Nikema and Carla need to look at. It seems like a good option because Dunkley Park's northernmost part is a half circle that could work well as a stage area. And the bottom part of the park is square, which could be a good place to meet people after the march. Just looking at the shape, it's not surprising that we'll have to combine all the thinking we've used so far in this episode to find the perimeter. For this park's perimeter, we'll have to figure out the perimeters of a partial rectangle and a partial circle, sort of like we did for the last 2 parks. Let's start with the partial rectangle. Based on the map online, the rectangle is 52 feet long and 34 feet wide, and the southern side, the western side, and the eastern side make up the perimeter of that section. Adding up those three sides, so far the perimeter is only 52 feet plus 52 feet plus 34 feet, which is 138 feet. But there's still that half-circle shaped part of the park. Fortunately, we're dealing with a half circle, so it's just half of whatever the full circle's circumference would be. This time, we can use the pattern we already figured out without having to draw more polygons inside the circle. The length of this circle's diameter is the same as the width of the rectangle, which is 34 feet. 34 feet wide times pi is about 106.81 feet, which gives us the entire circumference of the circle. We only have half the circle, so we divide by 2, which means half the circle's circumference is about 53.41 feet. And just like we did with the 4 Greensboro Corners Park, we can add up all the segments to get the total perimeter. The rectangular perimeter plus the semicircle's circumference gives us about 191.40 feet or 63.8 yards. To finish their planning, Nikema and Carla made a table to look across their park options. The 4 Greensboro Corners Park seems too small, and Revolution Park seems a bit too large, while Dunkley Park appears to be just right. In real life, if we need to know the perimeter of an object, it often won't be as easy as adding up all the sides. Sometimes we have to break down the problem and use logic to connect different pieces of the puzzle. No matter how wonky the shape is or how complicated the problem, math can help us find simpler examples to understand what's going on or look for patterns that show us more about the world. That's true even with a topic that sounds as simple as finding the distance around a shape. These calculations in geometric thinking tell us a lot. Like with closed spaces, like a trail surrounding a park, we can use the perimeter of a shape to get an idea of how much space is being used. And next time, instead of looking at the boundary of a shape, we'll think more about space, relationships, and how we can use math to understand what's inside a shape. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you liked this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.